All right, the idea for today is to find maximum minimums. It's kind of like, do you remember we did related rates, and they were pretty tricky. I don't know if you remember that. You find rates of change at a certain time, and yada yada. This is similar to that. This is very similar to that, in which you're going to write some kind of primary equation, and we might have to do some substitutions or something like that. But you want to write some main equation that we want to try to optimize, what they call it. Now we've done related rates with that, where we find like rates of change of the volume. How fast is the volume changing in a certain, a balloon or something like that. What optimization does is it says find out what the maximum volume could be, what the dimensions would be, so that we have a maximum or we might have a minimum, one of those two. So the first one we're going to take a look at is one of the more basic ones. Is going to be a box. Okay, so we're going to look at an open box. So let's go ahead and draw ourselves a box. Okay, so let's say we have a box like so. Should I have drawn that slower so you guys can copy my drawing? Sorry. Here we go. Hey. Step by step, draw a square. And then off of these 3 points, it doesn't really matter which points you go off of, but you just draw a line pretty much any angle you want. Once you draw your first one, the other ones are locked in. So you want to try to copy this line off of each vertice. So you want to have it parallel to this line and about the same length. So you want to go parallel and about the same length. Well, same thing off this point, parallel and same length, like so. This one's parallel and the same length. Parallel, same length. Oh, even harder. Parallel, same length.
Oh, God.
We're gonna die. The world is coming to an end. And by the way, just so I don't want any spoilers, okay? I haven't watched the Lost finale yet, so please don't spoil anything for me. I have a DVR, okay? So just don't want to hear about it. Don't.
He died.
Okay, earmuffs. Everybody dies, of course. The island will die. Let's just be quiet. So, anyways, please, just for my own sake, please be nice. Okay, so for this one, let's say we've got a box, and I want to try to find the dimensions of this box such that I maximize my volume. Okay. Now I'm given some parameters here. First off, I want the bottom here to be a square bottom. Okay. So I'm going to say this guy right here is x, and this guy right here is x. So the bottom has got to be a square. We want that. Okay. Now we want to know how big to make that square, how big it is, and then what the height is. This height is right here. And it's going to be an open top box, which means I'm not going to have a top on it. Okay, so just think of a cardboard box with no top in it. We can just dump stuff in it. Okay, or a tote or whatever you want to think about. Okay, I want to maximize the volume for this guy, which that tells you which equation you're going to be looking for, maximizing the volume based on having a square bottom, having a certain height, which we'll end up finding, and I also want to give the surface area here is going to equal 108. Okay, so the surface area, which means all the area on the surface. Now remember, there's no top on this; it's an open box. The surface area is going to be 108. Okay, and you call them inches squared or whatever you want to call it. It doesn't really matter there. So my surface area is 108. I want to maximize the volume, and I want to know what dimensions I have to have such that I maximize my volume. Okay. Now volume is all the stuff on the inside. Volume is going to be your primary equation here, and the primary equation is going to be the equation you want to take the derivative of. Okay. So I want to find the volume of this box, which is all the stuff on the inside, right? So how would you find the volume of this box right here? Yeah, there's a couple ways to do it. Yeah, length times width times height. There's a couple ways. Base times height. B being the area of the base. You can do whichever, but you can do the width and then the base. You can do lots of ways to do it. But anyways, if I always think about finding the area of the bottom and then multiplying it by the height. Okay, finding the area of the base, which would be x squared, and then multiplying that by the height of the box, which would be h, which is essentially length times width times height. That's essentially the same thing. Okay, so that's my volume equation. Okay, that's the volume. I want to maximize this equation right here such that my surface area equals 108. Okay, now the trick here, the question is I want to find the derivative of this because I'm looking for the maximum value. Okay, that's all we're going to be doing today pretty much is finding first derivatives and finding out where the maximum and minimum values are going to be. We're going to be able to cheat a little bit and I'll show you some tricks. But the volume for this is x squared times h. The problem is how would you put this on a calculator? This is a function with 3 variables in it, right? So our main problem that we're going to have on pretty much all these problems is trying to reduce the number of variables that are in there. Okay, so I want to maximize the volume, which means I want to find the derivative of the volume with respect to x. That's what I'm looking for, the derivative of my volume equation. That'll give me my critical numbers in which maximum minimums happen at. The problem is I have an equation with a couple variables, and I don't want to mess with h primes or There's no rates of change as far as this one. So I need to come up with another equation, a secondary equation, so that I can replace this h with something with x in it. Okay? Well, they give me my surface area is 108. Let's mess with that a little bit. Okay? Let's say I wanted to find the surface area of this piece right here. I'm just going to write down my equation right here. Surface area. Now I know the surface area is 108. How do I find the surface area of this box right here? The area on the surface.
It's minus the top because you don't have surface.
You don't have the top. Okay, so I don't have the top box. No, but the bottom piece is x squared. Is everybody okay with that?
Yeah.
Bottom piece is x squared, so I have an x squared. Plus, what about this front wall right here? What's the dimensions right here? xh, right? What's the dimensions of this guy? What about the back guy? And then the side guy? So I have 4xh's. So I have plus 4xh. Okay? So you have to generate your own equations on a lot of these, and most of them are either from geometry or from other classes that you've taken. But the surface area is going to equal this guy right here, x squared plus 4xh. And that, hopefully, it was pretty logical on where I got that. But what I want to do is say that my surface area, this equation right here, equals 108. So I have the equation 108 equals x squared plus 4xh. Okay, that's basically my constraints right there. I'm given a certain amount of material. I have 108 square inches to work with, and I want to maximize my volume for this guy. So what I'm looking for now is I'm actually trying to figure out what h is in this equation. I want to try to solve for h so that I can replace this guy with something with x in it. Okay, so your goal is to try to get this h by itself. Okay, so this one wouldn't be too bad to get the h. You just subtract the x squared. So 108 minus x squared equals 4xh. And then divide by 4x. Okay, so there's our equation. H equals 108 minus x squared over 4x. Okay, so that's the height depending on the x. So if I've got 108 square inches to work with, once I know what the x value is, that'll determine what my height is basically going to be. Well, now I'm going to plug it into this equation right here. I'm not quite to the dVdx yet. Sorry about that. So for my volume here, volume is going to equal x squared multiplied by h. H is all this stuff right here. So I got 108, minus x squared, and then divided by 4x. Which we can do a little bit of simplifying there, I think. So for my volume here, let's see, I can cancel one of these x's out, it looks like. So one of those x's will cancel out. And I can send this x into both those. So it would be 108x minus, I didn't need to do that, but that's okay. Minus x to the third, and then divide this by 4. Okay, so there's my volume equation. Okay, so the volume now, what I've done is I've written the volume equation in terms of x. So if I know what the x value is, I know what the volume is going to be. Okay, now my goal is to maximize this equation right here. I'm going to try and find the maximum volume for this equation. So let's go ahead and find the maximum. Okay, so if I find the maximum, find the derivative. Yeah. What's up?
Why did you cross out the 2 with the other one?
I had an x squared. I just canceled one x out. I had a 4x in the denominator, so
Okay, you turned it apart.
I just made it a 4. Yeah, because it was a 4x there. Yeah, so I just canceled one x out. So. All right, so now I want to, let's see, take the derivative of this and find out where my possible critical numbers are going to be. Okay, so I'm going to take v prime, find my critical numbers. So I got to take the derivative of this big mess. Can we cheat and just take the derivative of the numerator? Is that okay? Is that going to bug people? Now, how come I can do that? Oh, yeah. Thank you. Yep. Hey, it's Monday morning. A little bit of credit.
Why isn't the bottom 16 now?
Why isn't the bottom 16? Why would the bottom be 16? What? It's not like this was squared or anything, right?
Because you square the bottom proportion.
Okay. Yeah, I don't need to do that though. That's overkill. Well, I didn't use the quotient out there. Okay, fine. Is that the same? Is that okay with everybody? The constant of 4 on the bottom doesn't matter. Okay, it's just a constant. Don't need to worry about it. So I put the 1/4 in the front, or I just ignored that the 4 was there, because I really don't need to worry about that. Now, if I were to just do the derivative, or if I were to just divide the 4 into each one of those and make them decimals, it's still, you just use the power rule. So So I can just use the power rule on the inside, multiply it by a fourth, and call it good. Okay. So effectively, I just left the 4 on the bottom and ignored it. So. All right, cool. Now I want to find out where this equals 0, which isn't going to be too bad. Just set that equal to 0. And the 4 doesn't matter, honestly, on this problem, right? So I'm going to solve for 108 minus 3x squared equals 0. Because I essentially want the numerator to equal 0. The bottom can never equal 0, so I don't have to worry about that. So let's see. Move the 3x squared, so I get 108 equals 3x squared. Divide by 3. So 36, okay? 36 equals x squared. And so x equals plus or minus 6. Awesome. Okay, so I got my critical numbers. It's pretty good. I'm happy.
That worked out well.
Okay, I got my critical numbers plus or minus 6. So that means I have a maximum or minimum when x is 6 or when x is negative 6. And I want to just check those real quick. Okay, so let's see. Well, one of those I can just throw out right away, right? Wouldn't the negative 6 not make sense?
Yeah.
Right, because you're talking dimensions on a box. So I can pretty much take out the plus or minus. Don't need that, okay? So 6 is my only potential spot where this guy can maximize my my volume, okay? Now, I do want to double check just to make sure that is a maximum value. So you can do that a couple different ways. One way is do the first derivative test. Which do you guys remember the first derivative test? Maybe?
Yeah.
Summarize the first derivative test for me. What did it say?
That if it's negative and then it's positive, then it's the minimum. If positive, negative.
And we're talking increasing or decreasing,
Yes.
right? If it's increasing and then switches to decreasing, that's a maximum, okay? So if I want to check to see if this is a maximum volume, I'm just going to pick points right on either side of it, right? And I want to stay in my little range right here, but I'm going to pick points right on either side of it, like 5, right? If I were to plug in a 5, that'd be just on the left side of it. If I were to plug in a 5 into this number right here and see if it's increasing or decreasing, see if it's positive or negative, okay? We'll plug in a 5 right there. That'd be, what's that? That'd be 25 and 75, so that'd be positive, right? So I'm going to be positive on this side of it, right? So my graph is increasing. And then plug in a 7. If I plug in a 7, that's 49, 150 something, so negative. So it's going to be a negative on the other side. So since it switches, then I know that's going to be a maximum value. Okay? So I just did a quick first derivative test there. I found that the x is 6. That will maximize the volume for that particular one. Okay? Now, sometimes they do want you, if we're talking absolute max, absolute min, we can also use the endpoints. Basically, we could use, what if this x value right here was 0, right? Which is kind of a weird thing to think about. Or what if it was 1? Think about the very smallest number that you can make it to see if that would work for your volume. Well, if you were to plug a 0 into your derivative function, into your original function right here, you can see what the volume would actually be. Like actually plug in the endpoint. Plug in the 6, see what you get. Plug in the right endpoint, which you think the highest value is going to be, which I think is going to be like square root of 108 probably, because that would be the area of the base, and then the height wouldn't really be there. So I don't know. You could check the endpoints. There's nothing wrong with that, but that's generally what we're going to be going for. So, say it again.
So we kind of already did it, basically.
Yeah, we pretty much, exactly. All this stuff we've already done. It's just some applications of it, different ways to think about what it is exactly we're doing. So, and we're going to do, 3 or 4 of these and today. And like I said, I'm probably going to go to the bell, and then I'll give you the assignment, and you'll have all period Tuesday to work on it. So, that be the plan. And this stuff will be a little challenging, probably at first for you guys, but it's okay. All right, let's go ahead and talk about a little piece of paper. Yeah, square. Let me try that again. Okay, so it's a 2-dimensional shape. You guys should be able to do that. Hopefully. Hopefully that's the plan. All right, let's say I have some text on this paper.
Oh, whoa. We even have writing?
Yeah, that's words.
Okay.
Is it hole punch?
Text.
Braille.
Not hole punch. No,
Is it
no.
Braille?
Hole punch would be kind of fun, though.
But
Would it change surface area?
It would change the surface area. Good call. It would. That'd be pretty tricky to figure. Well, you just subtract them out, I guess. I don't know if that would change that. No, maybe it would. Just might. It just might. All right, let's say now I've got a piece of paper and I've got text on this paper. Now the actual print, I want the area of the print.
Oh, boy.
I want the area of the print to be 24 square inches.
Wait, so just the ink?
Just the ink. Okay, just the ink. I want the area of print. This area right here, I want that to be 24. I want that to be 24 square inches. Okay? That means if I were to just kind of drop lines down here, I want this inner part right here, maybe call this X and Y. It doesn't really matter which one you call it. Call this X, and then from here to here, I'm going to call this guy Y. Okay, so I have this little area here. Now I have margins on if you get a book, you have margins on the sides of it, right? And usually on the bottom margins, I'm going to call this a 1 inch and a 1 inch right here. And then we'll call this a 1.5 inch and a 1.5 inch. Okay, so that'll be the margins that I want. Now, assuming I want a 24 square inch area of print, that's how much print I want on each page, it's going to maximize the cost for me. I want to figure out what's the smallest amount of paper that I could actually use. Okay, so my goal here is to minimize the amount of paper used. Okay, so I want to use the smallest piece of paper that I possibly can, saving me money. Smallest piece of paper I possibly can, assuming that my margins are going to be 1.5 inches on top and bottom, 1 inch left and right, and I want 24 square inches of paper, print, so that I can get a certain number of pages and blah, blah, blah. Okay? So I want to minimize the amount of paper used. That's what I'm trying to minimize. Okay? Now, if I'm trying to minimize, that right there tells you what your primary equation is going to be. Okay? Whatever you're trying to minimize is what you want to make your primary equation. Well, I'm trying to minimize the amount of paper used. That means the actual entire whole piece of paper, I'm trying to make that as small as I can. So I'm trying to minimize area on this guy. Right? I'm trying to get the smallest area, the smallest piece of paper I possibly can get, between the entire piece of paper. So the area of this paper is just base times height. Pretty easy, right? So I got to take the area of the base right here, and then the length of the base and the length of the height, right? So what would the area be here? X plus 2 multiplied by Y plus 3.
Where'd you get 10?
Because X is from here to here, and I add 1 and 1 on each side of it. So my entire paper all the way across here is going to be an X plus 2. All the way from here to here. Shouldn't put an arrow there. Okay, so X plus 2 is that entire gap right there. On this entire gap, I've got Y for the inner part, for the text part, and then 1.5 and 1.5 give me 3. So I'm going to add 3 inches on my overall total there. So Y plus 3. So that's my area that I want to try to minimize. Okay, that's what they call your primary equation. It's the main equation you want to take the derivative of and be happy with. Okay. Now on this particular one, once again, I've got 2 variables. Most of the time you are. We got to switch it out. We got to make this 1 variable if we can. Well, they tell me that my area of my print is 24, right? So what would my secondary equation be? Yep, 24 equals X times Y. Yep. The inner print area is, you can think of that as a smaller piece of paper with no margins, right? That would be X times Y. So that would be the area of just the print on the inside. So X times Y is 24. That's going to be my margins that I want to look for, okay? So you want to solve for one of those equations. I usually solve for the Y. I like to have it all X's for some odd reason, just so my brain sees it better. So I would probably solve for Y on this equation and then plug that into the other, okay? So if I solve for Y here on this one, Y would equal 24 over X. Like so I can plug that in for this Y right here. So I can go X plus 2, and then 24 over X plus 3. Looks pretty good. So that's my area equation. Now, we can right now, we can take the derivative of this, or if we want to cheat a little bit, and I don't recommend cheating too much here, we could just put that on our calculator and hit minimum, maximum, right? We could do that, right? That's possible. So check your answers that way. Nothing wrong with doing that. So on this particular one, though, let's go ahead and do a little simplifying first here. Let's go ahead and FOIL this out and see what we get. So if we FOIL, X times 24 over X is 24, right? Plus, let's see, the outside here is 3X. Plus the inside is going to be a 48 over X. And then plus the last is going to be a 6. So I did a quick little FOIL. So my area equation is going to be, looks like 30 plus 3X plus 48 over X. Okay, which is a pretty clean equation to be taking derivatives of. It would have been kind of a mess to take it up at this level, right? So if we simplified it, it looks a little bit cleaner. Now I want to find the maximum or minimum, looking to minimize the paper size here. So I want to find the derivative of this, and hopefully it's going to be a minimum for me. Okay, so take the derivative. Derivative of this is going to be a 3, minus 48 over X squared.
Why is it my fault?
Because, okay, you're okay with this part, right?
Yeah.
Okay, good. So this right here, this is X to the negative 1. Right, so if I power rule that, that would be a negative 48 X to the negative 2. And I move my negative exponent back down. So it gets me back down to here.
Wait,
I power ruled 48x to the negative first. So I did a negative 1 in the front, and I dropped that by a power to get negative 2. So that's where I got the negative 48x and negative 2, and then I put that back on the bottom. All right, cool. So now I want to find out where this guy equals 0. Potentially undefined, right? But undefined might make this, you could find out where this is undefined, it'd be a 0, right? But that wouldn't really make sense for the problem, right? It'd be kind of weird to have a length 0 of paper, you know, as far as the print goes. So anyway, so we solved this for where this equals 0. So maybe move this term on the other side. We'd have 3 equals 48 over x squared. Probably multiply x squared on both sides, so 3x squared equals 48. Divide by 3, so you get x squared equals, what's 48 over 3? 16. Cool. Okay, so we're talking plus or minus 4. Okay, the minus doesn't really make sense, right? You guys are okay with that? So I would just say 4. So x equals 4, that's going to be the minimum size, so I can minimize my paper. That's so that I'll still get the right dimensions. Okay, so I get 4 is that guy, so that means that x is 4. So I've come up here, that means that this guy right here is a 4. My y value would have to be, well, if the area is 24, that means I got to be 6. So this guy is 6. So my paper size is going to be a 6 total here by 9 here. So a 6 by 9 piece of paper is going to minimize my paper usage, give them the margins that I want, and give them the square print of actual ink that I want. Okay? Make sense?
Wait, so the margin is like you.
The margins are fixed, right? We want the margins. The margins are usually, you know, pretty standard. Usually it's inch on these sides, inch and a half on this side. Unless you get large print, like my parents get large print books, you know. And the margins are a little smaller because they're, you know, words are like, there's like 5 words on a page, you know. The dog ran across the street. It's pretty bad.
Okay, so why couldn't you just, so you have to find the dimensions?
Yeah, exactly. Find how much. Find the paper size so that you're minimizing the area. You're minimizing the cost for us on that paper. So the area. Well, the area for this would be what? 54 would be the area of the paper, right?
Okay.
But they would probably ask something like, find the dimensions of the paper such that your area has been minimized. So that's probably what, or you use the least amount of paper. One of those.
I just think at the beginning I thought, well, why couldn't you just have 24 and then add the
All right, one more kind of tough one, and then I'll let you guys try one. Maybe. It's kind of moving it.
Take your color.
It's slanted.
Oh.
Okay. You keep on the roof.
Not yet. It's actually 2 telephone poles.
Oh.
A 12 foot and a 28 foot. They're 30 feet apart. And I'm going to attach from the top here. You know, they have those ground wires to go to the ground. You see those? What I want to, we're going to go to one central ground location. So we're going to go from here to here, and then we're going to go from here to here. And what I want to try to do is to minimize cost. I want to try to find the one spot where that's going to work. I want to find the one spot where I can only use one stake and one grounding post. And I want to try to minimize the amount of wire that I actually use. Okay, so that's what I'm searching for. Okay? So I know I'm so cheap. So what I want to do on this is I want to minimize the amount of wire that I used right here. Okay, so what I would probably do is make this length right here X. I want to know where exactly I have to put this stake, so that's what I'm minimizing my wire. Okay? Pictures would be nice. Usually they give you some pictures. So we'll say this guy right here is X. It's going to tell me how far from this post right here that I want to put the stake. And this side right here, well, if the whole thing is 30, like the 30 apart, this guy would have to be at 30 minus X. Okay, now what I want to do is I want to minimize the usage of wire here. That's what I'm searching for, is the minimum wire consumption right here. So the wire is going to be this piece right here plus this piece right here. So I already used X, so maybe I'll use like a Y and a Z or something like that. So my wire function is going to be a Y plus Z. and I want to try to minimize my W, minimize the amount of wire that I'm using. And you could have put whatever letters there you want. It doesn't really matter what letters you pick. So I want to minimize my W, and I want to try to do this in terms of X because I want to know where to put this post such that I'm using the least amount of wire right there. Okay? So what you got to do now is come up with another equation that somehow relates like Y with X if you can, right? Well, what equation could we build with this guy right here? Pythagorean theorem, right? So we can do what? X squared plus 12 squared equals Y squared. Right? That's Pythagorean theorem. So I could actually replace Y with something in terms of X, right? Which I could square root this guy. So I could square root this guy and square root this guy. So the square root of X squared plus 144, that equals Y. Now the plus or minus kind of goes away because we don't really want to think about a negative use of wire. So we can, for all intents and purposes, take that out of there. Okay? So I know that the Y part, my wire usage in terms of X, is going to be the square root of X squared plus 144. Plus, I got to find out what the Z is now. Okay? So I want to use the Z, and maybe I can try to connect the Z and the X somehow. Once again, Pythagorean theorem would be your friend here. So let's go ahead and use this right triangle and use Pythagorean theorem again.
Can we just call that X plus 12?
No.
Why?
B. Because you can't. Okay, fine. Be that way. So this is 12 and this is X, right? And you're saying there's one length between those, right? Well, what if this were 12 right here and this were X right here? Yeah, I mean, we know this is 90 right here. We do know that's 90, but unfortunately that doesn't work. I can show you the proof, but the proof's kind of cool, actually, for a right triangle. There's a couple proofs for the Pythagorean theorem. One was called the mousetrap proof, which you would take this, build a square off of this side, build a square off of this side, and it equals the square off of this guy. And if you add those two squares together, it gives you the third square. Yeah, that's the first. That's one. That's mousetrap. Let's see. Most common one probably was the Chinese one. It's kind of hard to draw. Yeah, the Chinese proof of the Pythagorean theorem. Yeah.
Whoa.
Wrong.
Oh, darn it.
No, I did it wrong. Hold on. This one's so hard for me to draw for some reason. I struggle drawing this one.
It's like getting glass.
Yeah, okay, so don't get sidetracked. Sorry. I'll draw it later. I'll draw it on the board. I will show it to you. The drawing on that's weird to get it first, but I'll get it. Ow, why not? Okay, so I got one equation, that's this guy, right? I need a second equation, that's this guy. So once again, Pythagorean theorem. So you're going to do what? 30 minus x squared plus 28 squared, and then equals z squared.
Oh, this is a new equation.
This is the secondary triangle. This is the bigger one on the right here.
Oh, no, it's...
Sorry. I was trying to get the triangle in the... Anyways, so square root that, right? So square both sides. And so z is going to equal the square root of this big mess right here, okay? So I've got the square root of 30 minus x squared, and then plus 28 squared. Okay, go ahead and take the derivative of that. Okay, or y equals on your calculator. Graph. Let's cheat on this one. This one's a bit nasty. So we'll cheat. Feel free to throw that on your calculator. I'll go ahead and do it on mine real quick here. So what do we got? We got the square root of x squared plus 144. No, you can't square it over that plus sign right there. Doesn't work. Can't do it. Can't do it. Yeah. Evil. Doesn't work. That drives me nuts. Oh, man, that drives me nuts. All right, square root of, let's see, 30 minus x squared, and then plus 28 squared.
So cool.
Beautiful graph. Awesome. Okay, let's find it. Sorry. Zoom fit. See if we can get close. Ooh, okay, that's okay. Once again, we're minimizing. We're trying to find the lowest x value. Or I'm sorry, we're trying to find the lowest wire usage, and we're looking for the x value such that that works. Okay. So if I were to take a look at this, Maybe this looks like parabolic later. Who knows? So let's go ahead and go a little bit more to the right and see what happens. Okay, so I'm going to go to my window. X max, let's go ahead and go to 30. Sure, why not? See what happens. Just curious. Yeah, that looks pretty good. So I kind of see a minimum value potentially in there. Maybe I want to go a little lower there, so go back to your window. And then Y minimum, let's go ahead and go like 30 to the minimum. Let's see if that looks a little better. Yeah, that's pretty good. Pretty happy with that. Okay, so now I want to find the minimum value there. AKA take the derivative, set it equal to 0. It'd be nasty. So we're going to go ahead and second calculate. And, number 3, minimum. Go on the left side. So go on the left side of where you think it is. Go on the right side. Guess. Yeah, guess. I love the guess part. So useless. So 9. So it looks like X is 9. So X is 9. When X is 9 right there, that's going to be a minimum value for us. At least it looks like on my graph right there. So I'm going to put it 9 feet away. So this guy being 9 feet away, this guy would then be 21 feet. And you can figure out what X and Y are. I'm sorry, what Y and Z are, so you can see actually how much wire was actually used. So, anyways, makes sense at least. So that's how you can cheat a little bit. X is 9 is where the minimum occurs, right? Well, 9 feet away from the 12-foot post is what I would say for your answer, or 21 feet away from the 28-foot post. Or it kind of depends on how they ask the question. They might also ask how much wire is going to be used now, right? Well, if you know how much wire, if you know that, let's see, this right here, this value is 9, you can do Pythagorean theorem to get Y now, right? Yeah. Or you can plug it back into this equation right here and get Y. So, and then, no, you would get this as 21. Do Pythagorean theorem with 21 and 28 to get this. So, you guys like just adding things together, don't you? It doesn't work. It doesn't work that way. Grumble, grumble. Grumble, grumble. That's a good one. I'm thinking Legend of Zelda now. Am I the only geek in here? Okay, I think we have time for one more. I'm giving you tomorrow to not do anything. Oh, man.
I told you I was going to go.
One day, and it's well deserved. Oh, man.
I told you.
Haley's way. No, that's a fake note. She forged it.
Haley, you're not allowed to talk about loss.
Yeah, no lost talk. I haven't seen it yet. It's on DVR. You can go 7-1. You can go 7 minutes without talking about it, right?
Haley can go
You
some.
better or you can.
Yeah, automatic, yeah. So. Oh, you broke the lead on my head.
About lost.
Let's see. Okay, so let's say I've got 4 feet of string or wire or anything that you want to use there. And I want to make a circle and I want to make a square, right? Or I want to make one circle, or I want to make one square using 4 feet of wire or string or whatever, and I'm trying to maximize my area for that. Okay, so I'm looking for some kind of maximum area of value. Okay, so now for the maximum combined area, that should tell you what your primary equation is. We're looking for an area that we're trying to maximize or take the derivative of. Okay, so we need to find the area equation for us. Okay, so the area. Oh, I was going to let you guys try this one. You want to try this one?
No.
Oh, let me draw a little picture. So I've got a square. And a circle. I want to add those together, and I want to maximize the area, and I can only use 4 feet of wire. Wow. Okay, so 4 feet is basically my constraints there. Okay, so 4 feet has got to get me all the way around the box and all the way around the circle, or maybe I just want to make one big box or make one big circle. I don't know. I want to maximize the area. I want to get the biggest area possible using 4 feet. Okay, so I got 4 feet, and I want to figure out what I should build.
Wait, so the wire's like around the circle?
The wires around the circle and the wires around the square.
Okay.
Exactly. Okay, try to write an area equation. Pi r squared is this guy. What's this guy? X squared, right? If you did x and x, right, area would be x squared. It's pretty good. Plus pi r squared. Not too bad. Okay, so I'm going to add those together. That's what I want to maximize. Okay, I'm maximizing my area right there. The problem is I have two variables. Okay, so and I haven't even used the 4 either, right? It's kind of weird when you do a math problem, you don't use all the numbers they give you. Strange. So we're going to use this 4 somehow. Okay, so how would I incorporate 4 into an equation? Remember, 4 goes around all this stuff.
4 equals x squared.
It's like the perimeter. There you go. The perimeter equals 4, and the perimeter has to go around the square and around the circle. Okay, so my perimeter equation, I'm going to write my perimeter equation. Right, what would the perimeter of the square be? 4x. Plus the pi d, but I probably want to do it as r, so 2 pi r, right? 2 pi r would be your circumference around the circle. Okay, so that's your perimeter, and we know the perimeter is going to equal 4. So we know this guy right here equals 4. Okay, so what I'd like to do is I'd like to solve for my radius and plug it into this equation and try to maximize my value there. Okay, so why don't you guys try to finish that? 4x is the perimeter of the square. Okay. X, that's 4 of them. And then the perimeter of a circle is the circumference, how far around it. That's 2 pi r. Okay? So I add those together. Okay, solve for r. No cheating and graphing the final answer here. Try to do it without graphing. Even though I showed you the shortcut. Oh, the way I did it there? So solve for r. Thank you. Sure. Go ahead. I don't know why you would, but yeah. Reduce it.
I mean, you went from 4 equals 4x.
I don't think I'll end up reducing that at all.
You know what I mean. I'm losing my words here.
I know what you mean. Okay, cool. We good? So that's our area equation. I plugged this into the radius right here.
The 2 minus 2x on the side. I can't.
Well, I subtracted 2x and divided by pi. Solve for r.
Yeah.
Well, I divided everything by 2 at the beginning because it looked nice. Looked prettier.
That's fine. Yeah.
Prettier. Oh, I'm running out of time. Okay, we're running out of time. So, ooh, do we have time? Oh, we so have time. It's going to be so good.
We so have time.
So simplify this a little bit here. X squared plus, let's see if I'm going to do a little trickery here. I'm going to square the pi, but there's one pi here, so I'm going to still have a pi on the denominator, and then I'll have the top squared, 2 minus 2x squared. So I would see the equation something looking like that. I'm thinking it's going to be easier to take my derivative in a moment. That's what I think. So take the derivative of that guy. It's going to be a 2x plus derivative of this guy. Let's say I'm going to move the 2 in the front. So there's going to be a 2 and then a 2 minus 2x raised to the first power. Divide this by pi. Multiply by the derivative of the inside, which is negative 2. So this is going to be a negative 4. So I've got a negative 4 like so. That's the first derivative. If you're not following, go back and try it later on your own. Okay? Now I want to find out where this equals 0. Nowhere where this is undefined. So I got to set this equal to 0. So if I set it equal to 0, right there, I would move this whole guy on the other side probably. So I'm making a positive. 4 and then 2 minus 2x over pi. And that would equal 2x. Then I would solve for x there. I'd probably distribute the 4 into both those, give me 8 minus 8x over pi. So I'm going to multiply by pi. So this would be 2 pi x. Something like that. Ooh, nasty decimals coming our way. Make this a decimal, move this 8x on the other side, and then divide, and you're good. You get your x, okay? I think x, when I read in the book, is 0.56.